Okay. So, let us continue with what we were discussing last time. We are trying to discuss some ways to select a computer system for a real time application, embedded real time application. How does one go about? So, basically the task consists of finding the parameters that are of interest and then evaluating different systems based on those metrics. Unlike general computer systems, where we have benchmarking programs and the manufacturers they quote with respect to those benchmarking programs. Here it is not so simple. We have to consider several parameters and then check the performance of the computer with respect to those parameters. And we had just discussed about determining the static parameters, I mean the deterministic static parameters, and then the latency parameters. The deterministic parameters, we are saying that whether the system behaves deterministically across different calls, timers are deterministic, etc. And then we are just starting to discuss about the latency aspects. So, let us proceed from that point. So, we are just starting to discuss this one, the latency benchmarks, where we will consider three parameters: the sync, message passing, and real time signals. So, the sync here will measure the overhead due to synchronization or the latency that is introduced due to the synchronization primitive. The simplest case will be, of course, that when a process requests for a resource which is declared as a semaphore. So, how much time does it take to acquire it? We will also consider message passing, which measures the overhead of sending data from one thread to another or from one process to another, depending on the operating system, because some operating systems support only threads on a process, and then there are multiple processes, and also threads, I mean data from thread of one process to thread of another process. And here the important parameters that we need to consider are the size of the data buffer size, and then the real time signals, which measure the latency of the signal once a signal is generated by one task. How much time does it take for the signal to get reported at the recipient? So, these are the three tests that we will discuss. One is that a task requests for a resource and then it waits for the resource is being used and it undergoes a context switch. So, through a system call, a task requests a resource, and how much time does it take for the context switch to occur? And here in the test 2, what we will do is that we will have two tasks, and task 1 requests a resource being held by task 2, and task 2 will request for a resource held by task 1. So, this is basically the round trip signaling latency. As you can see that task 1 is already holding resource and task 2 is holding a resource and it just calling that. And the third test that we will do is a low priority task has acquired a resource here R, and then a high priority task has requested for the resource. So, how much time the high priority task will take to acquire the resource? The high priority task will be delayed until the low priority task will release the resource, of course, but what about the medium priority tasks? If there are many medium priority tasks coming out which do not need the resource, then will it vary? So, we will have to test that. So, this third test is we have a low priority task holding a resource and then a high priority task requesting the resource, and in between there will be medium priority tasks which are executing, and what is the impact of that on the high priority task getting the required resource. So, in the test 1, we measure the latency of the semaphore system call. A single thread or a process waits for the semaphore. It makes a system call and waits for the semaphore. So, basically, if you see here, a single process makes a system call and it is not available, it just waits for it, and naturally it will undergo a context switch. So, how much time does it take for the context switch to occur? The test 2 uses 2 semaphores to signal between 2 threads, and here the threads are either in a single or 2 different processes. So, here if we consider the test 2 as T2, the time taken for the test 2 is T2, then the context switch time is basically T2 by 2 minus 1, because this is a, there are two calls involved here. Okay, there is a round trip signaling latency is involved here, and on the test 1 just it had requested one and then undergone the context switch. The test 3, it assesses the operating system's ability to deal with priority inversion, and we had discussed this one, that it just a low priority task is holding the resource and the high priority task is requesting it, and in between there are medium priority tasks which are generated. We can use a fixed duration processing loop to generate all these medium priority tasks and then check whether there is a difference in the time with respect to the high priority task getting the resource, because the low priority task takes a constant amount of time for its processing, and the high priority task should take that much time only to get the resource. But if we find that it varies depending on how many medium priority tasks run, etc., then we know that it is not handling the unbounded priority inversion. So, if a priority inversion occur, the time between the low priority task acquiring the resource and the high priority task receiving will be high. If unbounded priority inversions occur, then the time of the high priority task, the time at which the high priority task receives the resource, the delay it incurs in getting the resource will be high. But if the operating system has a mechanism to prevent priority inversion, basically the inheritance mechanism or the ceiling protocol or something, then the time will be very small. So, this also we can measure through a simple experiment. So far we have been looking at the operating system issues, looked at scheduler, task scheduler is the primary means through which a system tries to meet the constraints, the time constraints. And then we had seen that traditional operating systems are okay for soft real time applications, but for hard real time applications you can't use Unix and Windows, traditional Unix and Windows, we need to use real time operating systems. And then we had seen various types of real time operating systems, and then we had also mentioned about operating systems required for embedded applications. And then we had discussed about how to compare the performance of real time computers and operating systems through benchmarking. Now, we will just look at a few quiz before we proceed to the next topic. Let me just ask you a few questions. The first question is a true false question. The question statement is that the Linux kernel operates at a higher priority compared to real time tasks in RT Linux. What do you think? Why is that? So, what about others? False. Why is that? What's the justification?
It has to be preemptable. It has to be at lower priority because then only the real time task can meet the deadline.
Any other answer? Okay. So, the way RT Linux runs is that once on a Linux kernel you install RT Linux, it gets all the interrupts reported to it, isn't it? And also the traditional Linux runs as the low priority task, and the real time priority tasks run at a much higher priority, and it ensures the preemption of Linux priority, Linux kernel by this arrangement. So, irrespective of whether the actual code is preemptable or not, it becomes a task of the RT Linux, and therefore, it just can preempt it anytime, even if the kernel might be masking the interrupt, whatever it may be doing. You need not change the Linux kernel because it runs as a task of the RT Linux. It loses all its power to get the interrupts reported. It is reported via RT Linux. Is that okay? Now, let us look at the next question. If you are developing a small embedded application, which of the following real time operating systems would you use? One is QNX, Lynx, VRTX, Linux. So, why VRTX? You mean the size of the operating system? Any other answer? Okay, size is the answer, but see here VRTX is the host target operating system, QNX, Lynx, etc. These are self-host systems. So, you can't really run them on the target board, right? QNX you can't run it here. So, if it's a target board you are considering, then you can't test them with respect to QNX. One is you can't load it, and also it does not support a target board testing, isn't it? So, here VRTX is a host target system where you develop the application, run it on a host system, download it into a embedded board or a system on chip, and then test it. So, both size and also whether running it on a target board and testing is supported. Okay. Now, should a real time operating system support virtual memory? We had seen that many real time operating systems, they support virtual memory, some do not. When we looked at different operating system, the open source and the commercial, we had noticed this. but what do you think? I mean, what would be the advantage of having a virtual memory support on a real time operating system vis-a-vis what would be the disadvantage of having a virtual memory support in a real time operating system?
Virtual memory will allow you to have a multi-programming kind of thing and the memory protection and all that thing. Whereas
No, what do you mean by multi-programming?
Multiple programs residing in the memory.
No, that virtual memory is not a necessity for multi-programming. No, sorry, that is not a correct answer.
It can allow us to have smaller memory. With virtual memory, the memory requirement is smaller. The RAM size you require is smaller.
I mean, at what cost? You need a smaller RAM size at what cost?
The cost of starting.
No, no. What is the? I mean, it's just not just the RAM size. You need something else, isn't it?
Also, it can allow the protection.
Let's just he address his question. So, is it just you reduce the RAM size by using a virtual memory system, or is there something else you need when you use a virtual memory system? You need a hard disk, isn't it? You need a hard disk. Just having a less memory will not do. On a, so you are not reducing anything.
For storing the programs, we already have that.
No, no, no. See, normally none of the embedded applications have a, I mean, none means almost none. Very few may have hard disk. Usually they have a small flash drive or something. You can't implement a, I mean, on a small flash drive, you can't implement a virtual memory. So that's not a correct answer. That
it can allow for memory protection.
Okay. So one positive is that memory protection between the kernel processes and the processes among themselves is provided through virtual memory. Yeah, true. That is one of the advantages. Many advantages may be there. Yes, anybody would like to answer any other points as far as advantage is concerned?
Larger applications can be.
Okay. So, when you have soft real time applications or let us say a compiler debugger, let us say a self host system, it has to have virtual memories support for considering a self host system, because in a self host system we had looked at two different categories of real time operating system, the self host systems and the host target systems. If it is running only on the target board, virtual memory is not a necessity, but if it is a self host system, the application is also developed on it and also soft real time tasks if your system is required to handle, that is basically larger applications, large real time applications, then you need a virtual memory support, because compilers, debugger, or let us say email, networking, World Wide Web, all those things can run only if you have a virtual memory support. But if you are considering a very small application, then virtual memory is not a necessity. Yeah, that is also a point. For larger applications, you need virtual memory support, because there may be non-real time tasks and soft real time tasks. Now, what about the disadvantages?
So, the time may not be deterministic, like time for completion of processes, like because of swapping and page faults.
Okay. So, one is that the memory access time is not deterministic. Of course, that can be reduced through memory locking. Says that no, his answer is that when we use a virtual memory, because the page faults may occur, the memory access time can vary greatly depending on whether it is in the RAM or it is in the hard disk. So, of course, whenever a virtual memory based real time operating system is considered, and it is POSIX compliant, memory locking is provided. But what about any other disadvantage?
So
Yeah,
what is the
for many applications virtual memory is not required, just like small embedded systems. You can't really have the cost of supporting virtual memory there. Can't have a hard disk and all those processors supporting the virtual memory. You use a very simple processor, microcontroller or something. It would be very difficult to implement a virtual memory in a microcontroller. So, for very small applications, can't use a virtual memory. Any other points anybody would like to answer? Okay. So, let us look at the next question. It is a question slightly different from the previous one. What are the advantages and disadvantages? What are the pros and cons of having segmented memory scheme in a operating system? Yes, anybody would like to answer?
Assistant can be reduced if you have segmented memory.
Okay. So, the overhead of translation etc. is reduced, right? Virtual to physical translation etc. is reduced. Okay.
but sir, the number of processes will be limited to the
Size of the segment.
Okay. So, the number of processes may be limited to the segments, and any other points?
so like do we need to store the segment table also over here, so that will eat up space, like the mapping between the processes and which segment has been allocated to it.
Okay. So, maybe the implementation of how the segments are implemented, that will also determine, and also wastage of memory in a segmented space, right, segmented addressing. So, okay, those are the cons, but usable for small applications, can't use for large applications. Now, let us look at another question. Mention 4 important parameters that you can use to benchmark a real time operating system. So, trying to select real time operating systems from various vendors. Now, what parameters you can use to conduct your benchmark?
The interrupt latency time,
Okay, interrupt latency time, task switching time,
datagram throughput time.
datagram throughput time, anything else? Dispatch time. Okay, and also you can use the deterministic benchmarks and the latency benchmark. For example, how much time it remains in the kernel mode and non-preemptible, right, and whether the timers are deterministic. So, there are many aspects we considered. So, just only 4 asked here, but there are dozens of the aspects which you can consider to distinguish between real-time operating systems, depending on what is important for your application. If your application requires timers of 1 millisecond precision, that is an important consideration, then of course, you will like to consider timer jitter. Now, there is another question here. What problem would occur if in a certain real-time operating system, the system calls and function calls are indistinguishable, operate in the same way? There is no mode change, nothing. So, system call is the same as a function call. What problem can occur?
So protection features, like, so then there can be like
Not clear. What protection features?
Even the users will be working in privilege mode. They will be able to work in
Okay. Okay. So, when there is a system call and a function call, it means that there is only one mode, because the system calls are able to handle devices etc. in the user mode itself. See, when it is used as a function call, it is still in the user mode and it is able to do all the operations required. Then there is only one mode, and therefore, the kernel can be destroyed. I mean, the kernel can get corrupted while debugging or malicious programs and so on. So, it is basically only the kernel mode exists, no user mode, only the kernel mode exists. Then only the system call and function call will be indistinguishable, and in this case developing programs applications will become very difficult, and also malicious programs and so on. Okay. So, let us look at another question. If you have a uniprocessor system, can multithreading result in faster response time? See, only one processor is there, and if you use multithreading, will it result in any faster response time? So, some are saying yes, some are saying no. Let us just think about it little more.
We can have concurrent execution of certain part of code.
How? See, only one processor is there, no? A single threaded processor is there.
Talking about response time.
Yes.
It's different. It is response. Means it is not about the completion. It is only about the
Response. So, basically, if you have a program running as a multi-threaded processor program versus a ordinary program,
So it can be a faster response time, because if we have a situation where like the program has two threads, multi-threaded, and so the initial thread is blocked due to some IO or something.
yeah,
So then if it was not multi-threaded, then the response time would have
it will context switch. Yeah, exactly. See, the thing is that the question possibly we need to elaborate a little bit is that there are concurrent events that need to be handled. Just like you were saying that let us say you are doing a processing, concurrent processing, where it just undergone a blocking, one thread undergone a blocking, and then another thread can immediately start running. If you did not have any threads, then the entire process will block, isn't it? So, here definitely the time that it takes to run will be much smaller, because otherwise the entire thing would have blocked, isn't it?
But that
And
will not be the case always. It may be in some special cases.
So
In general, the multi-threading will
No,
only
no.
improve the throughput, not the response.
same
In
thing.
general, if we talk.
Same thing, response time is basically throughput, how fast it completes a job, and the job might involve several events and conditions. So, okay, so your let me just analyze your answer. So, the answer that you are trying to give there is that the average response time will improve, but not the worst case response time.
Yes.
Is it? Is it?
Yes.
Okay. Yes, true, but again see, possibly the question is bit ambiguous here. We could have also described the situation under which we are trying to measure the response time. Is it just the task running and doing disk IO, or is it just doing a simple arithmetic computation? So, the question is bit ambiguous, yes, correct, and your answer also that it can only the worst case response time, I mean the worst case response time will still remain the same, right? Only the average response time will improve in a multi-threading because of the blocking etc. looks reasonable. But of course, see, if you have another situation where we either implement through processes or through threads, if that was the question, then of course threading will take less time if we implement the equivalent solution using processes, threading response time will be faster. Is that okay with you? So, the question has a little bit of ambiguity, and that is why we have so many different answers for this. Now, this is a question: explain experiment to determine context switch time.
By reading the system clock, you can, whenever a process gets locked, before getting locked, should read the time from system clock.
But how will that happen? I mean, how do you determine that when it gets blocked? I mean, just making IO request, is it? Making a IO request or something, and then how do you know for the other task to start running? So, you have two tasks. He is mentioning an experiment where you have two tasks. One task just reports the time just before it issues a request for some semaphore or something, and then another task, as it starts, it reports the time. Yes, possible, but just think of some more experiments. That may not be very accurate time that you are measuring.
How they will report the time?
Sorry?
How they will report the time?
Report, it can be just written to a memory or something, which can be read by another task.
Read the system time and then
Yeah, read the, see, it basically writes into a memory location, one task. Another task writes into a memory location, a third task reads it and reports. Because if it prints it, that will take long time. You can just store in the memory location. Okay. Explain an experiment to determine the kernel blocking time. Yes, anyone? How good is the operating system with respect to real time performance, or how much time, maximum time it can block in the kernel mode?
similar to the previous one.
Just tell me what is the experiment.
Before issuing a system call,
Yes.
just read the.
So, before issuing a system call, read the time, clock get time. Okay, yes, and then
After this thing has finished, the system call is finished.
okay,
Then read the system time,
okay,
and then take this.
and then
Take this data.
but that takes the time, includes the time the system call takes to complete, isn't it? See, if you just make a system call and then before making the system call get the time, after system call you get the time, then it it also it includes basically the how much time the system call has taken to complete, but we are interested in kernel blocking time.
Some systems like we can register a system call, so kernel level function, so we can write the kernel level function so that like it makes a blocking call, and then
You mean you want to modify the kernel?
no, so like on some systems we can register like kernel level functions. So that very
No, not clear. The answer is not clear. What are you saying?
So like on some low level systems,
Yes.
very rudimentary. Like,
Yes.
so while we have the scope of modifying the bootloader and the kernel.
No, assume that, see, you are not going to change the kernel to measure the kernel blocking time. Assume that you have been given operating system.
Sir, in that what
You are running the operating system, not modifying it. You are not looking at the code. You are running the operating system.
Sir, when we are making a system call, the
Yes.
system call, let us make a system call like IO system call.
Yes.
In that case, the kernel will block it. Sir.
No. I mean, how does it?
For the IO to happen, till then it will be in kernel mode itself, but it cannot do other job because it will.
No. Suppose you are saying that give a time reading before making IO call, and then at the end of the IO call, is it?
Yes.
But then it just measures how much time it took to do IO. there is no kernel blocking reported at that time.
There are the timers.
Sorry?
Before blocking and after blocking.
No, how do you know when the kernel blocks? See, if you had this code, source code for kernel, etc., then you can check blocking by finding largest section, etc. No, that's ruled out. We are running the kernel, and then you just describe an experiment using which you can measure the kernel blocking time.
At that time, CPU must
block the kernel at our discretion. So that is
No, not that complicated. See, simple thing we had just discussed a few slides back, that you make a system call, okay, keep on making system call, and from another task which keeps on making system calls by the time this one makes system call, right. So, the completion of a call will depend on whether the other system call is being processed. If it is blocking, say a low priority task is making system call, and you have a high priority task trying to make some simple calls, right. Now, if the kernel is blocking, then of course, there will be a variation in the time. Sometimes when there is no system call to handle, it will complete in the shortest time, because this is the highest priority task. Now, if it was in the kernel mode, due to the other task calling, see, the other task in a loop is just keeping on calling the system call. So, if you notice a variation for the high priority task to complete, the system call to complete, then you know that the variation is due to a low priority task having made the system call, and that is the difference between the lowest time it completes and the highest time it completes gives the blocking time. Just think of it.
Task is making a system call.
Yes.
Why will the kernel block?
Because the system call makes it go into the kernel mode, right. So, if it is a blocking kernel,
But only higher priority task is running currently. So,
no, the highest priority task is before the highest priority task makes the call, this one is keeping on making the call, and the highest priority task once in a while it makes a call, and then you measure, and then after some time make another call, right. The highest priority task is once in a while making a call and then reporting the time. Low priority task is running in the background, just making system calls in a loop. So, just think of the experiment, you can refine the experiment, think of other experiments also, how you can measure the kernel blocking time. Okay, so we will start a new topic, which is real-time communications. So, we have seen so far some ideas about real-time operating systems, seen about the scheduling policy, resource sharing, commercial operating system, real-time POSIX, the features that need to be supported by a commercial operating system and few commercial operating system. Now, let us have some idea about real-time communications. Nowadays, we have applications that are becoming more complex, sometimes in distributed platforms, and sometimes they just need to communicate with another application somewhere, and many applications are inherently distributed because the data is getting generated somewhere at different places. The data is getting generated, and then the actuator is at some other place or at different places, and the data needs to be processed locally, because otherwise you will have to transmit too much of data. The data needs to be processed locally, sent to a controller, and the controller sends some signal to the actuator, which is also a processor, and then it does some computation and drives the actuator. So, in those situations, controller and many other situations, we can have a naturally distributed system, and then it also becomes cost effective to have many pieces of cheap hardware rather than having one centralized system. So, this is also another factor which is driving this distributed solutions. As far as the business sense is concerned, cost is concerned, it is much more cheaper to have several small pieces of hardware rather than one large piece of hardware. Now, let us try to find out what is this real time communication is about, what are its characteristics, how do we define, and so on, and how is it different from a traditional communication, because we know from a first level of course some basic ideas about computer communication. A traditional communication network provides best effort service. The best effort service is that it gives no guarantee on the time when it is the communication will occur. For example, let us look at Ethernet. So, it just tries to access the media and there is no guarantee when it will succeed in accessing the media. If the load is high, then it will take time for it to get the media and transmit, because of the collision, basic collision handling principle takes variable amount of time depending on the load. But we are talking of a communication mechanism where the maximum delay and the variation in delay are guaranteed. Okay. So, that is the simplest definition. We will see more elaborate definition of what is a real time communication. So, in a real time communication network, an application can make specific quality of service demands. See, in a traditional network, whatever is the best the network supports, it just gives that at that moment depending on the load and so on. It provides the best service that is possible under those situations. But here in a real time communication, the application, the real time application will make specific quality of service demand. For example, what is the maximum delay it can tolerate? What is the maximum loss rate, etc. So, these are the different quality of service. I mean, there are many more here, just examples of quality of service. So, that is a very basic definition. In a traditional network, the application has no control over the kind of service that will be delivered to it. Whatever best effort the network can provide, it just delivers that. Whereas, in a if we are talking of a real time communication being supported, the application should be able to request for a specific service or a service with a specific quality, and then the communication system should be able to support that quality of service. Then we have a real time communication, and we will elaborate this definition as we proceed. We are saying that the quality of service can be about maximum delay, it can be with respect to the loss, how much loss is tolerated. In a real time communication, once the network accepts a connection request with a specific quality of service requirement from the application, it has to guarantee the requested service quality. But let us elaborate this term service quality. What do we mean exactly by service quality? We are given some example of a service quality in terms of maximum delay with respect to the loss rate that can occur. We will consider 4 parameters for quality of service in our later discussions, the next and subsequent classes. One is the bandwidth that would be available to the communication. So, how much data it can transmit per unit time. the maximum transmission delay, the jitter, that is whatever delay is the maximum transmission delay, that should be constant preferably for some applications especially, because sometimes if it transmits in no time very fast and sometimes it takes the maximum transmission time, then for some applications we will have problem. So, the difference between the minimum delay and the maximum delay should be within certain bound that the application need, of course, the loss rate. So, let us look at some ideas about this and the kind of applications that might make such requests. Okay, and also the blocking probability. For example, you are trying to initiate a call, but it could not be accommodated by the system, by the communication system, because it does not have resources to support. So, you have said that certain delay bandwidth is required, and then it might so happen that the system does not have those resources. So, then your call will block, and if it blocks too often, then your application will suffer, right. For applications, the blocking probability may be almost 0 for some applications, right. Some applications tolerate no blocking probability, some other applications might tolerate some amount of blocking probability. Okay, let us contrast first with the definition of a real-time communication with a traditional communication. Let us look at a traditional application like a FTP, email, etc. We know that they have reliability requirement, isn't it? If you do a FTP or email and on the other side you receive a corrupted document, nobody will accept that, isn't it? You FTP'd a 1 gigabyte file and then find that part of it is corrupted, then it is as good as not downloading that file, isn't it? And similar with respect to email, you sent a large email and then found that garbled up many parts, you won't like that network. So, for soft real time applications also reliability can be a concern. We had said that reliability is also a concern for hard real time communication. Actually, if you look at the network protocols, much of the complexity of the traditional network protocols arise from need for loss free communication. So, all the traditional communication, whether you talk of TCP protocol, the idea is to provide loss free communication. So, how do they ensure loss free communication? Sorry? Because the media is lossy. There can be a, no, at the physical level, there may be a, let us say lightning occurred, or let us say electric spark occurred and the data got corrupted, but finally it has to be ensured that it is a loss free. So, how do traditional protocols ensure loss free communication? Error correcting. Error correcting is not really usable. See, he said error correction mechanism, but normally error correcting code has too much of overhead. I think in the first level course you would see that error correction mechanism is very expensive in terms of the amount of overhead, in terms of data that you need to transmit for correction. Correction is extremely expensive and difficult, but what can easily be done is error detection and retransmission. Correction codes are expensive, not usable for a typical communication. So, what typically done in a traditional network is error detection and retransmission. That is how it works. At various levels the errors are checked, the physical level, at the packet level and so on, because packets may be lost. Even though the lower level ensures that the data is sent, let us say physical level, you have checked through correction, finally you find that the packet is lost. But how can that happen? that at the lowest level, the physical level, you have ensured that no corrections, no corruption, and there has been retransmission at the lowest level. So, how can at a higher level, at a packet network level, you find that the packet has been lost? No, all those corruption they have taken care at the lowest level. Whenever there is a corrupt data, that is retransmitted, the lowest level, physical level.
Yeah, after getting the prayer from the lower level, we will have certain headers to form it as a packet in network layer. So certain extra headers are added. So
that's a packet definition, but how can packets get lost? Because the media access control, the MAC protocol will ensure that the packets have been, the data that is sent, the frames basically, the frames have been transmitted successfully, that is ensured. But at the packet level, there may be loss in packets. How can it happen? It's a very first level course, question that I am asking. At the frame level, you find that frames have been delivered correctly. But at packet level, there is a loss. You shouldn't again have a detection and correction mechanism at the packet level. You know that TCP, etc., they keep count of the number of packet. They have a serial number, isn't it? So, why is that necessary? Because lower level, you have ensured that there are no errors.
If the order of the frames changes,
Reordering is not a problem. Okay, this is a very fast level question. The packets might have been dropped to intermediate nodes. So, this is the end-to-end communication, right? So, there are many intermediate nodes that might be involved, and somewhere because of the load considerations, packet might have been dropped on intermediate nodes, and then finally at the destination, even though at the lower level you have ensured that there are no corruption, at the end to end you see that packets are missed. Okay. So, we will not really diverse to that extent. And even if you look at soft real time communications, FTP, etc., even the packet delay and average throughput are also important parameters, because if it takes long amount of time and the throughput is very low, that won't also be acceptable for FTP or email. But what are not important for soft real time communication is the worst case packet delay, the jitter, and the worst case throughput. What we are concerned is the average case delay and throughput. Even jitter is not a concern for soft real time communication. So, the worst case delay, throughput are not a concern for a soft real time application. What is of concern to a soft real time communication is the average packet delay, average throughput, and jitter is normally not a concern for soft real time application. On the other hand, if we have a television transmission occurring as a non-interactive manner, which are typical televisions, here there are strict bounds on the jitter, but insensitive to delay. Do you agree with this? See, in a typical television, see nowadays television have become interactive, you might have seen that. But let us not consider the interactive television, but when the transmission is occurring one-sided, these are there are bounds on the jitter, but insensitive to delay. Do you agree with this?
why should it be insensitive to delay?
Okay, that is what I am asking basically, that why should the traditional televisions be insensitive to delay, but they do not tolerate jitter.
Jitter portion is covered, but the insensitive to delay.
Okay, not
So like since they are like soft real time or like no timing returns is there, so even if the broadcast is after a few seconds,
yeah.
it will not matter.
Yeah, see if all the let us say you are looking at a movie or something. So, it does not matter when exactly it was transmitted from the antenna and when you received, or let us say when it was supposed to be broadcast and when you exactly receive it, as long as it is within few seconds or minutes.
That case is true if all the frames are having the same delay.
Exactly.
Suppose one frame is coming in time.
No, that is jitter. So, we are saying that it does not tolerate jitter, where some frames are coming very fast, some are not coming fast, right. But if all the frames are equally delayed, then the viewer will not feel anything. That is what we are saying. Same thing we have just written down, that in a traditional television, we require stringent bounds on jitter, that is, different frames should not incur different amounts of delay, but the maximum delay is not a problem. I mean, the amount of delay, as long as it is constant, it is not a problem. It can be 1 second, it can be 5 seconds, does not matter. But the jitter, even if it is few milliseconds, 50 milliseconds, you will immediately notice the picture getting disturbed. So, we will stop here and we will continue in the next class from this point. Okay, thank you.